Hello everyone, I welcome all of you in my sixth lecture of heat and mass transfer subject. So before I start this today's class, I'd like to revise the previous lessons of heat and mass transfer. So in our previous classes, we discussed about heat, we discussed about temperature, different units of temperature, different units of heat. So in temperature, we have seen it's nothing but a property of property of body which identifies or which defines that heat transfer from which direction to which direction. And heat means this is the energy which flows from one direction to another direction due to temperature difference. So if there is any temperature difference, when it's a high temperature to low temperature, heat energy flows. And there we have seen heat, their unit of heat is calorie and joule. So 1 joule equals to 4.2 calorie, and units of temperatures are degree Celsius or degree Fahrenheit or Kelvin. And there we discussed about different modes of heat transfer: conduction, convection, and radiation. So conduction means there is a medium is solid, and convection their medium is liquid or gas, and in radiation there no medium is required. So in conduction, we have seen that solid, molecules of the solid body are closely packed with each other. So that's why if molecule vibrates due to temperature disturbance, then the adjacent molecules start to vibrate, and gradually the heat transfer from one direction to another direction. And in convection heat transfer, we have seen that liquid or gas, the molecules are not closely packed. There some distance between due to the distance between the molecules, the heat transfer rate is very low. That means it takes more time to transfer or carry the heat from one place to another. So there in convections we have seen free convection and forced convection, and in radiation we have found one formula, Stephen Boltzmann law. So this all we discussed, and then we have found general heat conduction equation for in Cartesian coordinate, then in cylindrical coordinate, and in spherical coordinate. And lastly, we discussed one-dimensional heat transfer of slab with no heat generation and with in steady state, and for cylinder also. For slab, the formula of heat transfer was, yes, tell me. Yes, it was Q equals to K into A T1 minus T2 by L, and in cylinder the formula is Q equals to 2 pi K L delta T by ln of R2 by R1. So up to this we discussed. So now going further. So here we have one-dimensional steady state without heat generation in sphere body. So first we find out the mode of heat transfer. So it's a solid or liquid or gas. Yes, it's a solid body, means its conduction heat transfer occurs. Now in spherical conduction, we already know the general heat conduction equation, and the formula already we know. So I'll just read out: del 2 T by del R2 plus 2 by R del T by del R plus 1 by R square sin square theta del 2 T by del phi 2 plus 1 by R square sin theta del theta of sin theta del theta plus Qg by K equals to 1 by alpha del T by del T into dt. Now as per condition, you see here the condition is first one dimensional. So here three dimensions are there: r, phi and theta. So this r we consider and theta and phi we neglect. So if we consider only r, then only del t by del r or del 2 t by del r terms will be present. Next condition is steady state. So steady state means this del T by del T, the rate of this temperature change will be negligible, will be zero. And the last conditions we can take here: without heat generation, means Qg value will be zero. So if we consider all these assumptions or all these conditions, then the last the final equations we get here: del 2 T by del R2 plus 2 by R into del T by del R equals to 0. Now in the both side, if we multiply with r, then what you get? Yes, r into d2t by dr2 plus dt by dr equals to, sorry, 2 into dt by dr equals to 0. Now in the next line, again if we multiply with r in the both side of this equation, then we get r square d2t by dr2 plus 2r into dt by dr. Now this whole on our left hand side we can rewrite as ddr of r square dt by dr equals to 0. Now how do you get this? So we can simplify this term r square d2t by, sorry, dt by dr. So if we differentiate with respect to r, then what do you get? ddr of r square into dt by dr. So we know the formula of ddx of ab. So what is the formula of ddx of a into b? A into db by dx plus b into dA by dx. Now here same way I can write r square into ddr of dtdr plus dtdr into ddr of r square. So next line we can write r square ddr of dtdr means double derivative, so it's become d2t by dr2 plus dtdr multiply with ddr of r square. So ddx of x to the power n, the formula is n into x to the power n minus 1. So here r square will become in 2r. So finally we get r square into d2t t by dr2 plus 2r into dtdr. So this whole term in the left hand side I can rewrite as ddr of r square into dt by dr. Now if we integrate this equation in the left hand both sides, right hand side, then we get integration of ddr of r square dt by dr into dr equals to 0. So finally we get r square into dt by dr equals to c1. So c1 is a constant. Now we can cross multiply and we get here dt equals to c1 into dr by r square. Now if we integrate both sides once more, then we can write integration of dt equals to c1 into integration of dr by r square. So this c1 is constant, so I can take this out of the function. Next, integration of dt equals to c1 into, so 1 by r square we can write as r to the power minus 2 into dr. Now again if we continue, integration of dt equals to c1 into, so integration of x to the power minus x to the power n, the formula is x to the power n plus 1 by n plus 1. So here also you see here x is related compared to r and n is compared to minus 2. So if we compare and if we rewrite the formula, so we get here c1 into within bracket r to the power minus 2 plus 1 divided by, yes tell me, minus 2 plus 1 into plus c2. So c2 is one more constant. So finally we get here t equals to c1 into r to the power minus 1 divided by minus 1 plus c2. So finally t equals to minus c1 divided by r plus c2. Now you see we have two unknowns, c1 and c2. So how do you get this value of c1 and c2? So for this again same way we need boundary conditions. So how do you get the boundary conditions? Now if you look at the picture, you have in the picture you have two radius. Okay, so one sphere you have taken and that sphere it has inner radius and it has outer radius. So inner radius it is r1 and outer radius it is r2. Now already we have taken the assumption that at r1 radius the temperature is T1 and at R2 radius the temperature is R2. So this is my boundary conditions. Now here you can see if R equals to R1 then T equals to T1. Again in the second case if R is R2 then temperature becomes T2. So if we put the first boundary conditions in the equation 2, so we get here T1 equals to minus C1 divided by, in place of R we put R1 plus C2. And in the second time if we put the second boundary condition in the equation 2, we get here T2 equals to minus C1 by, in place of R now you put R2 plus C2. Now we can solve this third and fifth and sixth equation. So how do you solve this? So if we do 5 minus 6 So in the left hand side we get T1 minus T2 equals to, in the right hand side if we subtract this right hand side we get here minus C1 by R1 plus C2 minus within bracket minus C1 by R2 plus C2. So finally we get T1 minus T2 equals to minus C1 by R1 plus C2, then plus C1 by R2, then minus C2. So if we remove the bracket. Yeah. So next step if we continue, so T1 minus T2 equals to, now we take this minus C1 common, within bracket it comes 1 by R1 minus 1 by R2. So from here we can easily calculate the value of C1. So what is the value of C1? It's coming minus T1 minus T2 by 1 by R1 minus 1 by R2. Now we can see from the equations we had two unknowns. One is C1, one was C2. So till now we calculated only C1. Now again we have to calculate the value of C2. So how do you get this? So next simple, just put the value of C1 into the equation number 5, because you are solving 5th and 6th equation. So you can put either 5 or 6. So here I am giving this C1 value into 5th equation. So I can write this T1 equals to minus C1 by R1 plus C2. Now if I put the value of my C1, so it gets, it looks like T1 equals to minus, within bracket, minus T1 minus T2 divided by 1 by R1 minus 1 by R2 into 1 by R1 plus C2. So from here T1 equals to, we can write T1 minus T2 divided by 1 by R1 minus 1 by R2 into 1 by R1 plus C2. So finally we get C2 equals to T1 minus, within bracket, T1 minus T2 by 1 by R1 minus 1 by R2 bracket closed into 1 by R1. So now we get the value of C1 and C2. So now we put the value of C1 and C2 in the equation number 2 and we rewrite the equation T equals to minus C1 by R plus C2. So we get here T equals to minus, within bracket, minus T1 minus T2 by 1 by R1 minus 1 by R2 into 1 by R plus C2. So the value of C2 was, I already got here, T1 minus T1 minus T2 by 1 by R1 minus 1 by R2 into 1 by R1. So finally we get here T equals to T1 plus T1 minus T2 divided by 1 by R1 minus 1 by R2 bracket closed 1 by R minus T1 minus T2 by 1 by R1 minus 1 by R2 into bracket closed 1 by R1. So this whole equation is called as temperature distribution equation. Now the importance of this temperature distribution equation is, at any point of at any point of location you can find out the value of temperature of spherical body. So as we know, as you can recall, in cylindrical or slab body also we calculated the value of temperature distribution equation. So here also you see, here R1 and R2 both are known, only unknown is temperature and only unknown is R. So if I give you the value of R and if I ask you to calculate the value of temperature, yes, you can calculate. So at any point of R value or radius, you can calculate the value of temperature of spherical product or body. So now we have another one question is heat transfer. So how much heat is transferred? Yes, we can calculate from which law? Fourier's, Newton's law, or Stephen Boltzmann. It is a conduction mode. So we'll follow Fourier's law of heat conduction. So here is the formula: Q equals to minus K into A into dt by dx. Now your variable is R, so I can change the equation as Q equals to minus K into A dt by dr. Now here we have already calculated the value of dt by dr. So from equation number 1, if we follow this, so we can write R square into dt by dr equals to C1. So the dt by dr equals to, it comes C1 by R square. Now already we had the value of C1, so I'll just put the value of C1 here. So we get here dt by dr equals to minus T1 minus T2 by 1 by R1 minus 1 by R2 into 1 by R square. Now from Fourier's law, Q equals to minus K into A into dt by dr. So let's put the value of dt by dr. So we get here Q equals to minus K into A into within bracket minus T1 minus T2 by 1 by R1 minus 1 by R2 bracket closed 1 by R square. So here already we know the value of area of sphere. So the area of sphere is 4 pi r square. So I can put the value of 4 pi r square in the area in the a place. So it comes Q equals to K into 4 pi r square into T1 minus T2 divided by R2 minus R1 by R1 R2 into 1 by R square. So next line, this R square and R square we can cancel from up and down. So finally we get here, finally the formula of heat transfer for spherical product is Q equals to 4 pi K R1 into R2 into T1 minus T2 divided by R2 minus R1. So if you look at this equation, you can see there is a T1 minus T2 term. So as we know that T1 minus T2 is nothing but the temperature difference between the spherical product or spherical body. So due to this temperature difference, heat transfer occurs. So let's end this class. So before ending the class, I'd like to revise the today's class. So today we discussed about the heat transfer of spherical body, and the formula of heat transfer we get here Q equals to 4 pi K R1 R2 into T1 minus T2 by R2 minus R1. So same way we can say the formula of heat transfer for slab. The formula is Q equals to K into A T1 minus T2 by L, and for cylinder, yes, tell me, Q equals to 2 pi K into L T1 minus T2 by ln of R2 by R1. So these three heat transfer you must remember for solving numericals in your next classes. Okay, thank you.